Alright, hello everybody. Today we are going over the fourth lesson of Unit 2, which is on the structure of metals and alloys. Today you should be able to represent a metallic solid and or alloy using a model to show essential characteristics of the structure and interactions present in the substance. Today's understanding is that metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons. Also, that interstitial alloys form between atoms of different radii, where smaller atoms fill in the interstitial spaces between the larger atoms. And then substitutional alloys form between atoms of comparable radius, where one atom substitutes for the other in a lattice. Although ionic and covalent bonds are more common, metallic bonding describes a lattice of cations surrounded by a sea of valence electrons. So the nucleus and the core electrons of the metal are going to stay in place, but the valence electrons are going to be mobile. Now, let's try to visualize in our heads what this is actually saying. So let's compare two metals. Let's compare the iron 2+ ion and the aluminum ion. Now, when we talk about a metallic bond, the actual bond is happening between the cation and the electrons that it got rid of to become the cation. So, for example, we know if we have iron, a sample of iron, and those irons are a 2+ charge, that means for every iron that became a cation of 2+ charge, it lost 2 electrons. So if we have this small sample of 6 iron cations, that means we have 6 times 2, or 12 electrons that are now floating around in between all of these cations. So the actual bond is the bond between the delocalized free-moving valence electrons and the positively charged cations that are in this lattice structure. Now, let's move over to what aluminum looks like. If we were to have a sample of solid aluminum metal, we know aluminum forms a +3 charge when it becomes a cation. So if all 6 of these aluminum atoms became 3+ ions, that means we'd have 3 + 6, or 18 valence electrons. Now we have 2 samples of 2 different metals, both having 6 cations, but the aluminum metal will be stronger in terms of metallic bonding because there are more free floating electrons to attract to those positive cations. So when we're talking about properties of metals, you need to know that metals can conduct electricity because of those freely moving delocalized electrons. So since those electrons are not localized to a specific spot, they can move wherever they want, they can conduct electricity because that electric charge can go through all of those electrons. Now, metals are also malleable and ductile, and that's because metals are less rigid and they can be bent and spun into wires. Metals can also bond with each other and become something called alloys. Alloys can be formed when 2 metals are in their liquid form and then are mixed together. And then when the mixture cools, it becomes an alloy. So there are 2 different types of alloy, a substitutional alloy and an interstitial alloy. The main difference is between the radius of the 2 metals that you are combining. So if the radius of the 2 or more metals that you're combining are the same or similar, that's going to be a substitutional alloy. If you are looking at different metals and they are severely different in size, meaning one is bigger than the other, then you will have an interstitial alloy, which is shown on the right there. So a student ran an experiment to see if the solids in the table conduct electricity. Explain the results the students saw. So you can see that solid iron did conduct electricity, but solid iron 2 chloride did not conduct electricity. So we know from our definition of metallic bonding that it would make sense that solid iron conducted electricity because it has those delocalized electrons that can carry current through the metal. However, when we have solid iron 2 chloride, all of those electrons in those ionic bonds are localized in the ionic bond between iron and chlorine, so it cannot conduct electricity as a solid. Then part B says, is there anything that could have been different in this experiment to see the FeCl2 sample conduct electricity? Now we know when we're talking about ionic solids that as a solid, it is in that crystalline lattice structure where all of the electrons are localized to ionic bonds. Now what happens if we dissolve that in water? Well, if we dissolve FeCl2 in a beaker of water, ionic solids are soluble in water, which means when you put that solid in water, they are going to dissociate into their constituent ions. So now instead of in an individual FeCl2 compound, I actually have one iron ion for every 2 chlorine ions floating around in that sample of water. And now, because those ions are freely moving, they can now conduct electricity. So the answer to B would be if you dissolved FeCl2 into water, the aqueous solution would then conduct electricity because those ions are now able to move and flow and actually conduct that current. All right, so let's try a FRQ question that has to do with alloys. It says white gold is a common alloy of gold and palladium that is often used in jewelry. The atomic radii of the metals are given in the table above. A particular ring is made from an alloy that is 75% gold and 25% palladium. Using the box below, draw a particle level diagram of the solid alloy consisting of 12 atoms with a representative proportion of atom types. Your diagram should clearly indicate whether the alloy is interstitial or substitutional. Use empty circles for gold and shaded circles for palladium. So we know that we are going to draw the alloy, but the first thing we need to do is figure out if it's interstitial or substitutional. And we do that by looking at the atomic radius. We can see that the radii of the two metals are very similar. So since they are of similar size, we're going to have a substitutional alloy, which means they're pretty much all the same size. So we know this question wants 12 atoms. So I'm going to go ahead and draw 12 circles to represent the 12 atoms. And then it said that it's 75% gold and 25% palladium. So 75% of 12 is going to be 9. So we're going to have 9 gold atoms and then 3 palladium atoms. Now, because this is a substitutional alloy, you're just going to pick 3 random circles to shade in. You don't want them all in the same region. So you're just going to pick 3 random ones. I'm going to pick this one, and this one. So part A of this FRQ is worth 2 points. You got 1 point for doing the correct number of each atom. So if you had 9 empty circles and 3 shaded circles, that was 1 point. And then you got another point for showing an acceptable arrangement, which means they were the same size and all the shaded ones weren't together. So that was worth 2 points. And then to wrap up this lesson, I just wanted to leave this table here for you because we are kind of over talking about the different types of solids. And so this is a great little review for you before we move on into Lewis structures. I hope you have a great day.